So we're beginning section 19, standard error of the mean. So let's suppose there's a large population, and you can see this large population of Michigan with a mean of 80 on a standardized test. And let's say that the researcher doesn't have any of this information, but wants to estimate the mean of the population by testing only a sample. So the researcher draws a random sample, gives the test to just the sample, and the question is, will they correctly estimate the population mean as exactly 80? Well, in all likelihood, no, because random sampling introduces chance errors known as sampling error. And of course, as you've learned previously, these errors can affect the results. So let's look at effects of random sampling error on results in the long run. So let's look at the researcher has drawn a sample from the population that has a population mean of 80. So they drew a random sample of 60 from the population, tested the participants, and computed the mean for the sample, and they calculated a 70. They repeated this, and they drew another random sample of 60 from the same population with a population mean of 80, tested the participants, and computed the mean for the second sample, and found that the second sample had a sample mean of 75. They then drew a third random sample of 60 from the same population, tested the participants, computed the mean for the third sample, and found that the third sample mean was 85. And they did it a fourth time. And now we have a sample of 60. We tested and computed the means for the sample, and we got a sample mean of 90. Now, you see that the population mean is 80. And now these are the hypothetical results for the first 4 random samples drawn by the researcher. None of these random the sample means, are equal to the population mean of 80. None of them. Some were too high, some were too low, but when we look at the average of all 4 of these sample means, we actually find that it is in fact the population mean. Well, the hypothetical researcher would have a very large number of means. So they've had 4 samples, which we have, and they just continue to have an indefinite number of other samples, which then creates what we know as a sampling distribution of means. So that means that you have a huge distribution of sampling means, of the sample means. So one other aspect of sampling distribution is when we talk about a central limit theorem, the CLT. The CLT states that the sampling distribution of means is normal in shape. And if you remember back in section 7, we talked about what a normal distribution looks like, what a normal curve looks like. So you see this on the slide, and many of you may recall that. Now, we also know that the standard error of the mean, noted above, is a standard deviation of the sampling distribution, and it is actually a very useful statistic. You will see in the next slide that how this works. So now in practice, and we've already talked about this, and we've said that a researcher usually draws a single sample, they test it, and they calculate the mean. But what the researcher doesn't know while they're doing any of this, the researcher does not know the certain value they are not certain of the value of the population mean. They really do not know the value of the standard error of the mean that would have been obtained if they had repeatedly sampled an indefinite number of times. So they don't know any of this information, but what they do know is that the larger the sample, the smaller standard error of the mean, and this is because larger samples have greater precision, and the less the variability in a population, the smaller the standard error of the mean, because sampling from less variable populations yields more precise results. Now, if you are still kind of confused about some of this, please go back and review section 18 to review the relationship between sample size and precision, and section 18 to review the relationship between variability and precision. Now, what we can also say is that some of the statistical theory, and given these previous two facts, the statisticians have developed a formula for estimating the standard error of the mean based only on the information the researcher has. So let's see if we can calculate the standard error of the mean. We'll show how this is reported after it's calculated for a set of data. So we've calculated the standard error of the mean, and we have a 2.00. If you see, we have a sample mean of 75, a standard deviation of 16, an N of 64. Now let's look at this, because what we have, the standard error of the mean, is what we call a margin of error. Now, the margin of error is what researchers should use when interpreting the sample mean of 75. Now, the standard error of the mean is a type of a standard distribution, and if you remember back from the study of standard distribution earlier in the book, in section 11, you would recall about 68% of the cases in a normal distribution lie within one standard deviation unit of the mean. And so because the standard error of the mean in example 1 equals 2 points, we would expect about 68% of the all sample means to lie within the 2 points of the true population mean. So the standard error of the mean indicates that 68% of all sample means lie within 2 points of the true population mean. So now let's consider a practical use of the standard error of the mean. So now we can use it to actually build a 68% confidence interval, or a CI, for the mean. Now remember, here is what we have from our example 1. And what we do is we take our standard error of the mean is 2. We have our mean of 75, and we subtract the standard error of the mean from the mean, and we have 73. And we also add 2.00 to the mean of 75, and we have a 77. Now these two numbers, the 73 and the 77, are the limits of the 68% confidence interval for the mean of 75. So to account for sampling errors, there is a more reliable estimate of the true population mean, in that it is between 73 and 77. And we can actually say that we are 68% confident that the true population mean lies between 73 and 77. Now, let's talk briefly about reporting. So when we report, we can report the single value, such as the mean of 75, as an estimate of a population mean based on a sample, and we call that a point estimate of the mean. We also can report the limits of the confidence interval, which was 73 and 77, and we can say, the confidence interval is 73 to 77. And so we have an interval estimate of the mean. Usually we report both the point estimate and the interval estimate, or we can report the point estimate as well as the associated standard error of the mean, so that the consumer of the research, the reader of the research, can calculate their own interval estimate. It is not necessary that we do that for them. Now let's look at table 19.1, example 2. Now what this does is it actually shows you several things. It shows you that, first of all, it's more common for researchers to report a 95% or a 99% confidence interval instead of a 68% confidence interval. And think about it, you're much happier to be able to say something with 95% confidence or 99% confidence instead of 68% confidence, correct? So when there are several groups, the intervals are often reported in a table. And if you'll look at group A, and we're talking about group A, you see we have an N. So we have the number of participants at 128. We have a mean of 75. We have a standard deviation of 16. But we can report with 95% confidence. We have a 95% confidence that the true mean, the true population mean, lies between 72.23 and 77.77. So notice we're still not certain of the value of the true population mean because that's just 128 participants, which are a random sample of the population. But we do have a result, the 95% confidence interval, in which we can say we have a lot of confidence that we are presenting an accurate estimate of the population mean. So size is important. Now remember, our small confidence intervals are desirable. The size of the population is an important factor in the computation of the standard error of the mean, and by using reasonably large samples, researchers can minimize the size of the standard error of the mean and obtain confidence intervals that are reasonably small. Now one thing that we also want to cover is that our confidence interval validity, that our confidence intervals are only valid when our means are obtained with random sampling. So, our confidence intervals assist in interpreting means that are subject to random errors. They cannot take bias into account. And if there is a bias creating the errors, there is no general technique for estimating the amount of error created by the bias. And therefore, it's not possible to calculate meaningful confidence intervals. And so this is one of the reasons why we stress very much on using random samples whenever possible.